morning, everybody. Welcome back. Tomorrow, right, test autopsy for exam 4. This is the last unit, right? This is it. We've got, including this week, we've got 4 weeks before finals week. You're taking your last exam in this class on the last week of classes, like not during finals week. So we really only have 3 more weeks of content and then a test week. It's going to be, we're doing chapters a little bit out of order. So we're back to chapter 11 now. And then we'll do 12, 13, 14, and 15. I know that sounds like a lot of content in 3 weeks. Yeah, counting them up. But I cut out quite a bit of content in thermodynamics because thermodynamics is dumb. And we should spend as little time in it as we possibly can. But what is not done is fluids, and we're going to be doing fluid physics. So we're going to do fluid physics, and then we're going to apply what we learned about fluids to the messy business of thermodynamics, temperatures, heats, all that sort of stuff. If you've been in chemistry, then it's going to sound pretty familiar. But let's dive right in. So we're going to apply everything we know, all of our toolboxes, to fluids. And what's a fluid? Can anybody give me an example of a fluid? So any gas and liquid. So just to be clear, right? When a physicist says fluid, we are not just thinking about water. It's the air in this room. Okay, that is also a fluid. Basically, physicists think of solids and then everything else, right? And we'll talk about the different states of matter when we get into thermodynamics. But just to be clear, when I say fluid, now, we will use the example of water a lot. It's just a natural, it's a common everyday experience, and so we will refer back to water all the time, but just realize it can be any liquid or gas. The problem with any fluid, up to this point, we've been talking about objects that have a certain mass. The tungsten cube had a mass, the car had a mass, the billiard ball had a mass, the bowling ball had a mass. With a fluid, right, if I take a cup of water and I start pouring it, the mass of that fluid changes as it goes places. And so it's awkward to have to keep track of the mass of a fluid. And by the same token, it's kind of awkward to keep track of the volume of a fluid. Because, again, it can change depending on, if the river flows into a big lake or a small pool or whatever, right? So we're going to shift just a little bit, okay? The language or the idea that we're going to keep track, it's going to still be like a mass. It's going to show up everywhere, but it's going to be an idea, the thing that doesn't change. No matter how much water I have, whether I have an Olympic-sized swimming pool or a coffee cup's worth of water, there is one thing that is always the same if it's water. What is it? It's density, right? So we use the Greek letter rho, and that's supposed to be like kind of like a curly P-ish looking thing, right? It looks like a P, but a little bit more italics or something like that. And the symbol rho in physics we use for volume density. So in this case, it would be volume mass density. In other words, take the total mass, divide by the total volume, you are always going to get this number. Again, no matter how much of it we have. And this is true for all materials. Assuming the material is like uniform, like you have a chunk of aluminum that's really big versus, and I take a little chunk out of that piece of a big aluminum, I'm going to have the same density. So density becomes the thing, right? Kind of like mass that doesn't change as the fluid goes from one point to another. Again, with the caveat that the deeper you go in the ocean, the denser the water becomes because it gets compressed under the weight of the ocean. Same thing with air. The density of air here at sea level is much higher than it is. We go higher up in the atmosphere. So we'll have to do a little bit of physics land type, well, there's no friction and the density stays the same. Unless we tell you otherwise, and then it's pretty easy to factor in those changes. What are the units of density here? What are units of mass? Not grams, close, kilograms, right? It's that one unit that doesn't follow, it's got the prefix on it, right? So the units here are kilograms, and then what would a volume be? Meters, not squared, cubed, right? Okay, because a volume is not just a surface area. We also got to do the height of it, right? Length times width times height. So this would be a kilogram per meter cubed, and that is the standard unit for density in physics. So for those of you that if you haven't had chemistry, congratulations, okay? You are unsullied by chemistry, okay? For those of you that have had chemistry, I'm sorry. Because you measured units when it comes to fluids and thermodynamics, you used a slightly different system. What were the units of density in chemistry? Grams per, well, that was the pressure. Grams per cubic centimeters. Do you remember that? Grams per cubic, grams per milliliter. Yeah, this is starting to bring back some post-traumatic stress disorder from chemistry, right? So chemists and physicists, we both use the standard system of units, the metric system of units. But chemists have kind of standardized everything off of grams per cubic centimeter, whereas physicists, we stick with kilograms per cubic meter, okay? So first place you might get messed up here. For example, the density of water is a defined thing. I should use a triple equal sign here because that means defined as. It means we're just picking this. Everything else gets scaled to this, okay? In physics, it's 1,000 kilograms per cubic meter. They probably taught you in chemistry that it's 1 gram per cubic centimeter or 1 gram per milliliter. Those are exactly the same number. It's the same density described in different systems of units. It's just chemists typically aren't dealing with a cubic meter, right, of water. That would be a cube, that wide, that tall, and that deep, right? They just don't use that much of their solutions and things like that, right? They're using very, very tiny amounts, maybe a beaker full, something like that. So it's a little bit more convenient for them to scale everything to grams per cubic centimeter. In physics, we're typically talking about atmospheres and oceans and rivers and things like that, and we don't want to be stuck in milliliters per cubic centimeter. We want to use the actual standard unit. So all of the equations that we use in physics, again, I taught you this over and over again, right? Standard units in means standard units out. If you're using all of the standard units, you'll be safe. The equations know how to deal with all the units. All right, so that's kind of the first adjustment that we're going to have to make when it comes to fluids. The second adjustment comes from talking about force. We know force is a push or a pull. And again, when it comes to fluids, it can be really awkward to have to talk about the force of every individual water molecule that, let's say you got a garden hose and you're spraying something, right? It can be really kind of awkward to talk about the individual forces of the water molecules. We want to talk about it kind of in bulk. And so the way we do that is we define, and now this is an actual capital letter P. Sorry, I'm not responsible for any of this symbology. Okay? We define something called pressure. Okay? And I know you're probably familiar with pressure. It's kind of all around us, like tire pressure, and you've probably encountered pressures in chemistry. I already heard atmospheres already. Pressure is an amount of force that is concentrated or spread out over an area. So pressure is affected by the amount of a push or a pull on an object. But we need to also take into consideration how focused that force is, okay, on an amount of area. If I take a force and I spread it out over the entire surface of the board, that's not very much pressure. But if I take that same amount of force and I concentrate it down to a little point, that's going to be a lot of pressure. How are nails shaped? Sort of a funny question, but let's think about it. What do nails look like?
Hammer nails or fingernails?
The hammer nails.
Kind of pointy.
Kind of pointy, right? They kind of go, they have a point, right? And then they have like a flat head on top. Kind of depends on the nail, right? Okay. So hammer comes down, applies a force, right? An impact to the top of that nail head, right? That force gets transferred through the nail and then ends up over a very small area. In other words, nails don't look like this, right? Right? You don't hammer in the flat top, right? We're trying to concentrate the force into a small area, giving a very large pressure, and it's that pressure that drives apart the wood fibers and allows the nail to go in. Knives. In order to use a knife effectively and safely, it needs to be very sharp. People cut themselves when the knife is dull. Why do people cut themselves with dull knives? In order to cause the cut to happen, you have to apply more force. The difference between a dull knife and a sharp knife is very slight. So a knife blade usually comes up to a nice peak, okay? And believe it or not, a lot of dull knives, they're not like flat on top, okay? What happens is the tip gets kind of bent over. And I don't know if you've ever watched a cooking show or been to a restaurant where they're being too fancy, but have you ever seen like a chef take that steel rod and they whoosh, 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 the knife up and down the steel rod, okay? They're doing it wrong, okay? That is called a honing steel, and it has a very specific function. It's supposed to take a knife whose tip has been bent over. It's still sharp. It's just been bent over, and it's supposed to bring it back into alignment. And the way you do it is by holding it at a specific angle, using very deliberate strokes, okay, to bring that knife back into. Now, the knife needs to originally be sharpened. If you got a flat knife, you need to sharpen that edge out. But as it gets used, it usually gets bent to one side or the other, and the honing steel brings it back. But people injure themselves with dull knives, especially knives that are sort of bent over at the tip, because they're applying a lot of pressure and with a lot of force to get that same amount of pressure out. There's more area in contact with the food right here, but you can achieve the same pressure, the same amount of cut, say through the tomato, which I'm convinced are grown in wetsuits nowadays. You ever had a tomato where you're trying to cut it and it just kind of smooshes out, right? Sharpen your knife. You can cut a tomato with way less actual force, same amount of pressure, because you're able to take all of that force and concentrate it down right to that knife's sharp tip. So pressure is our way that we're going to deal with this idea of force in a fluid. And I want to talk more about that pressure, but before we get there, let's talk units again. So units of force. What are the units of force? Yeah, it's a Newton, right? And units of area, you guessed it earlier wrong for volume. Meters squared, right? It's length times the width. So the Newton per meter squared gets a new name called a Pascal. Okay? They use the symbol PA to label that. So this is where it gets, well, the units kind of just go back, okay? Pascal is the SI unit. It's the one that we are going to use in physics, okay? But I'm going to bet that you have run across the atmosphere. If you've taken any kind of chemistry anywhere in your schooling, you probably ran across an atmosphere. What's an atmosphere? In terms of like pressure, what are they talking about? Yeah, like at sea level. What's going on? Okay, the air pressure, where does it come from?
The amount of air particles packed into a given space.
Good. Does air have weight? Yeah, it does. The gas molecules have mass. They're being pulled on by gravity. So the force would be the weight of air. And then that weight of air is concentrated over some kind of area. The atmosphere is the unit that they often use in chemistry to talk about the pressure exerted by a column of air at sea level. Take the entire weight of, say, air above you, all the way up to the Kármán line, the internationally decreed 100-kilometer height where space begins, even though the atmosphere goes way past that, okay? And you take the total weight of a column of air sitting above you, and you will have an atmosphere, assuming you are at sea level. We're slightly higher than sea level here, so we're a little bit less. But that atmosphere happens to be equal to 1.01 times 10 to the 5th Pascal. So there again is that SI unit that we're going to be using in physics. The atmosphere is not an SI unit. But again, it's okay, great, it's 101,000 pascals. What does that mean, Mr. Balogh? Well, in the stupid system of units, you may have heard of 14.7 pounds per square inch. What are pounds? It's a unit of what? It's weight, it's force, okay? The pound is the unit of force in the imperial system of units, okay? Inches squared, what is that? It's an area, isn't it? Okay, so here we've got a force per area, and an atmosphere is 14.7 pounds per square inch. So we're 200 feet above sea level here in Fresno, which is basically the same as being at sea level, so I'll just assume sea level. That means that for every square inch of area on the surface of your body, there is approximately 15 pounds of force. The average surface area for a human being is 2,000 square inches. How many pounds of atmospheric force are on you? If it's 15 pounds per square inch about, and there's 2,000 square inches, how do you find the total force? Multiply. Multiply 15 times 2,000. Isn't that 30,000 pounds? No wonder it was hard to get up this morning. I got 30, I'm feeling the pressure. The pressure. Why do you not feel that pressure?
It's coming in from all directions, so it cancels out.
Ooh, okay, so like some of it's coming from this way and some of it's coming from that way. You definitely don't want to like unbalance the pressure.
But the inside of you is.
Ah, very good, right? The pressure's inside and out, right? You were conceived and born into this pressure environment. The pressure inside your body is 14.7 pounds per square inch. The pressure outside your body is 14.7 pounds per square inch. So the net pressure, the difference in pressure inside to out is what? 0. And you shouldn't be feeling any of that pressure. Unless, of course, you say jump into the ocean or a lake or something like that, or a backyard swimming pool, and you start swimming down. You start swimming down, what happens to your ears? Yeah, you start to feel the squeeze, that pressure on your ears. What have you just done? When you jumped in the water, what did you do? And by doing that, what have you done? Well, you've locked in a pressure. What pressure? You've just closed all the holes in your body. Now what? You go jump into the water. There's 14.7 pounds per square inch inside you. But as you get deeper and deeper into the water, what's going to happen to the weight of the water that's above you? It's going to increase, isn't it? So the pressure in the water increases with depth. And if you get to a point where it's 30 pounds per square inch outside of you, but only 15 pounds per square inch outside versus inside, you're going to feel the pressure difference. You're going to feel it on your eardrum. And that membrane's going to go, I don't like that. And it's going to hurt. And then if you've been trained, you'll know you can equalize the pressure in your sinuses with that of the outside by squeezing your nose and go, right? And you kind of push air from your lungs into your head, into your sinuses to get your ears to equalize. And then that pain goes away. So pressure, right, and pressure difference are important. We have to define something now, okay? Because I brought up this idea, right, that the amount of pressure in a fluid has to do with like the weight of the fluid that's above an object. But here's a really, really amazing thing, okay? The pressure, say in the ocean or a pool or anything like that, is going to be a result of the ambient pressure, like the air pressure above the surface of the water, plus the pressure that comes from the water itself. And amazingly, that pressure is only going to depend really on one thing. Technically three, but functionally one thing. So first of all, the pressure is going to depend on the density of the fluid that you happen to be in. So again, as a picture, what am I picturing here? I'm picturing like a swimming pool or something like that. It's got some water in it. There's atmospheric pressure above it, okay? And so we've got like the 101,000 pascals, right? The 1 atmosphere, the 14.7 pounds per square inch. We've got that sitting above that, right? It's not vacuum up there, it's air pressure. And then you dive down to the bottom of the pool. I want to make it very clear, you are not dead. I know sometimes my drawings, right, make it imply things, but you're not. You're just down there, okay? And you're down inside of this pool at a depth, h. In physics, we think of the height of the column of fluid above the point that we're trying to measure the pressure at, okay? So you'll hear me call it depth, and I'll use the symbol h, okay? Anyway. All right, so notice that the pressure at the bottom of that pool depends on what the pool is filled with. If you're swimming in honey, ethyl alcohol, carbon tetrachloride, whatever floats your boat, okay? The density of the fluid matters. As does the planet that you happen to be on. But we're going to be on Earth, so that, isn't really. So functionally, these two things don't really change, right? Okay? The depth is really going to be the pressure is really going to be determined by the depth. Notice what's missing here.
The lowercase p.
No, we've got the lowercase, we got rho, we got g, we got h. But there's something missing pressure is not determined by this, which is kind of crazy. What's this? This is a Hoover Dam with Lake Mead behind it, okay? The Hoover Dam, famously where we store the Allspark. Right? So, no, nobody knows that reference. 3 people know that reference. Okay, fine. Transformers. So Lake Mead, okay, so Hoover Dam, big dam, 800 feet, top to bottom, okay? Lake Mead on the other side, really, well, not so deep anymore, we lost a lot of water behind it. This is an older picture. But at its fullest extent, Lake Mead would go for like 120 miles upstream, like just a phenomenal amount of water stored on the Colorado River for Las Vegas and communities in Arizona, all kinds, right? Just a ton of water. The pressure at the bottom of Lake Mead, 800 feet below the surface, only depends on the depth and not the total amount of fluid. It's rho g h. It's not rho g, oh my gosh, there's so much water here. It's just the depth. So, if I were swimming, let's say I was scuba diving in a lake in Yosemite, Tenaya Lake, it's about 8,000 feet above sea level. Tenaya Lake's got a depth of like 1,000 feet, okay? And I go to the bottom, which you should not do because that's really deep, okay? And we measure the pressure at the bottom of Tenaya Lake, okay? And then we go to the middle of the Pacific Ocean, and we measure the depth at 100 feet. Which one's going to have more pressure, Tenaya Lake or the ocean? It's Tenaya Lake, because it's deeper. The total amount of fluid does not matter when it comes to pressure. And it really kind of flies in the face, because we would think of like, oh, there's a lot of water, there must be a lot of pressure. There isn't. So there's a thought experiment where, like, if you, somebody's tried this, it doesn't work. If you drop a garden hose down the face of the dam here, right, on the air side, 800-foot garden hose, okay, and you plugged up the bottom and you started filling the top with water, okay, the pressure at the bottom of that garden hose, okay, would be equal to the pressure on the other side of the dam down 800 feet below the surface. The total amount of water doesn't matter. Now, the reason this doesn't work, it's kind of a thought experiment, not a practical one, is because the garden hose would explode before. Garden hoses can really only hold about 150 psi, pounds per square inch, before they rupture, okay? And we would exceed that long before we were able to fill that garden hose. But again, it's not the total amount of fluid that matters. All that matters for calculating pressure is the vertical depth above the point that you are trying to measure. See if I can prove it to you with an experiment. I got video, not quiz, but I am going to ask you to turn and talk to your neighbor. So listen up.
This is an electronic pressure gauge with a pressure sensor at the bottom. Blowing into the sensor through a tube increases the pressure and drives a bar graph display whose length is proportional to the pressure at the sensor.
That means that it's always going to be at the surface of the water.
In a column of water changes with increasing depth.
Do you see how the sensor is calibrated so that it always lights up at the surface?
The display shows that the pressure increases in direct proportion to the depth. What will happen to the display if we tip the water column at an angle? Okay, so they didn't explain this very well, right? The lights on the display are calibrated so that they always show like the depth of the water, right? It's measuring pressure, so as they go in deeper and deeper, the lights get longer and longer, but it's calibrated to always be the level of the water. Okay, they're going to take this whole tube, and they're not going to dump any water out, so the total amount of water is going to stay the same. They're going to take this whole tube, and they're just going to tilt it on its side. Again, they're not going to lose any water. Turn to your neighbor and discuss with them whether you think the length of that bar thing is going to increase, decrease, or stay the same. Go.
All right, by show of hands, how many of you say that the bar is going to increase or get bigger? How many of you say it's going to decrease and get smaller? Oh, a lot of you. And the rest of you are stay the same? Stay the same? All right, let's see what happens.
This is an electron.
No, I already did that part.
Tipping the column of water reduces the pressure reading. The length of the display is still equal
Watch.
to the vertical depth of water above the sensor, as shown by this line.
What determines pressure? Depth. Direct vertical distance between where you're measuring the pressure and where the surface of the water is. Did it matter that there wasn't water like directly above that point? No. All that mattered was the vertical height between where the surface of the fluid was and where the pressure sensor was. It's only height. It's only that depth, that height of water above that point, plus adding on atmospheric pressure that you've gotta be worried about. Okay, so let's talk about another specter, as it were, when it comes to measuring pressure. And this has everything to do with the devices that we use to measure pressure. So, one of the things so when you go into the doctor, right, for whatever the thing, they have to check to make sure that you are alive, right? And one of the many things that they do to make sure that you are still alive is they take your blood pressure, right? I'm always joking with the nurses after they take, am I still alive? And they just look at me like, what? It's like, am I alive? They're like, yeah. I was like, are you sure? Anyway, when they measure blood pressure, they usually give you two numbers. Anybody know what the normal versions are? The average or acceptable blood pressure? 120 over 80. Okay? You wanna have a good time? The nurses sometime, okay? Ask them what units that pressure is being expressed in. I've watched nurses panic when I've asked that question. Does anybody know what the units are? An old unit. So in this case, it would be millimeters of mercury. Okay? You actually read it right on the dial. And half of my nurses have gone, huh? And then just looked at it, oh, millimeters of mercury. And then they stop and they go, what's a millimeter of mercury? And I was like, I'm so glad you asked that question. Sit down, I've got a lecture for you. Millimeters of mercury, okay? Used to be the way that they measured pressures. Old barometers, things that measured air pressure. You would take a glass tube and you would suck all the air out, pull a vacuum on it. And then you would fill it with, you would have a pool of mercury, liquid metal, and you'd put the glass tube in it. And the air pressure would push down on the surface of mercury and push the column of mercury up into the glass tube. And they would literally just measure the height in millimeters of mercury that thing went. And as the atmospheric pressure changed, it would go up and down. As they made pressure gauges, they just carried over the unit, millimeters of mercury. If you ever watch a weather forecast, they might tell you about atmospheric pressures, and here in the United States, they will say that the atmospheric pressure is 30.01 inches of mercury. Okay? Basically, an atmosphere is 30 inches of mercury or 760 millimeters of mercury. These are all kind of strange pressure units. Pressure's been measured for a long time, which is why it has a lot of these strange units. But we're going to use pascals in here. But let's talk about this for just a second. 120 over 80. What's the systolic? That's the one on top, right? What's the systolic pressure measuring? What's that?
First heartbeat.
Okay, so the way blood pressure is measured is you put a tourniquet on somebody's arm. Important safety tip, never take the blood pressure around the neck. Okay. Put a tourniquet around the arm. A tourniquet does what? Stops the blood flow, right? That's where that pressure of that cuff comes in and squeezes off the blood flow through this vein right here, okay? And then, right, you start letting off. Nowadays, it's all fancy-dancy computer AI machine learning things, right, okay? But back in the old days, when I was young and the dinosaurs roamed the earth, we had to listen with the stethoscope, and what we were listening for as we let off that pressure is for that first spurt of blood back through that vein, okay? And you would listen and you would hear a rush of blood as it came through, and you would watch the pressure dial as you first heard that rush. So that represents the sort of peak pressure the heart is exerting to push blood through this artificial constriction, okay? And then the bottom number, the systolic over dystolic, did I get that right? Diastolic? Thank you, I can have its words, right? This number, right, is you're listening, you hear the swoosh, swoosh, swoosh of the blood, and then that kind of swoosh, it dies out. You don't hear the turbulent, and at that point where you don't hear the swoosh anymore, that's the relaxed pressure, okay? So basically a heart squeezes, right, contracts, it's much more complicated than this. I know anatomy and physiology students, there's a lot more going on, but I'm simplifying. The heart goes, right, pushing that blood out, you measure that pressure that the heart is putting out, and then the heart relaxes. And this is kind of that like relaxation pressure. All right, so why am I talking about this? That pressure is measured by a gauge. And gauges always tell you a difference. In other words, when we feel the tires on our car, okay, you can go look at the sidewall of a tire. I brought a picture. Brought a picture of the sidewall of the tire. Okay, so you'll see some numbers and things on the sidewall of the tire. Okay, and there'll be lots of information here. Okay, but notice, right? They're giving the tire pressure here in kilopascals and pounds per square inch. They're saying 44. We'll just do pounds per square inch for now. Okay, so this is the maximum pressure this tire should be inflated to. Okay, any more than that, and you're risking a blowout. Okay, so when a tire is flat and you try to put a pressure gauge on it, what will the gauge read? It'll read 0, right? Okay. But when the tire goes flat, is all of the air sucked out of it and you get a perfect vacuum? No. What is a pressure gauge trying to tell you? What is the actual pressure inside of a flat tire?
1.01 by 10 to the 5th pascals.
It's equal to the ambient pressure. It's 14.7 pounds per square inch outside the tire, and it's 14.7 pounds per square inch inside the tire, and that's when the gauge will read 0. The blood pressure cuff reads 0 when there's no pressure on it, but actually there's atmospheric pressure on it. And so the 120 millimeters of mercury is above the normal ambient pressure that is all around us. So when it comes to gauge and absolute pressure, you do need to be careful. And problems will tell you, they'll say, the gauge pressure on this submarine, or the gauge pressure, a pressure gauge reads blah, blah, blah when a tire is being filled, right? They're trying to give you a big hint, right? That a device, a pressure gauge is measuring, and pressure gauges always give you the difference between what we call the absolute pressure, the real pressure, the total pressure, and then some kind of atmospheric pressure, right? This P naught is usually the ambient or atmospheric pressure Like there's lots of pressure units, right? Okay. So maybe not. I might be wrong on torr. You know what? Let's just take torr off of there, right? Is it 1,000, 100? I never remember what it is. Okay. There's just so many different pressure units out there, and you can look up what 1 atmosphere is for all the different pressure units. In here, we're going to use pascals. And maybe we'll drop 1 atmosphere on you, like say 1 atmosphere. Well, then you immediately know, okay, that's 1.01 times 10 to the 5th pascals. And you just move on with your life, okay? But just realize a pressure gauge will always tell you the difference between what the real pressure is and what atmospheric or ambient, the surrounding pressure, happens to be. Yeah?
Couple questions. The thing you wrote, LAT, what's the subscript about it?
It's atmosphere. It's 1 atmosphere. Sorry. It's the number 1.
ATM.
And then ATM. Yeah, sorry.
So then P0, that's ambient pressure?
Yeah, like reference pressure, ambient pressure, atmospheric pressure. I'm not being real specific here because, it does fluctuate. But we won't worry too much about any of those fluctuations. So if I wanted to know what the actual pressure inside of a tire is, at its most tires you recommend to inflate to 35 pounds per square inch. And by the way, how do you know how much to fill your tires? Some of you are looking at me like, I fill my tires? Check your tire pressure. Why do you want good tire pressure?
Even tread wear.
Even tread wear, gas mileage. The first 2 things always mentioned deal with money, right? Safety. Safety third, right? So yeah, check your tire pressures, okay? And make sure, the way you look on the side of the tire. For some reason, the United States federal government thinks it's important that there be a sticker on the inside of your door jamb that tells this tire pressure, but that only applies if you keep the same tires on your car. Nobody does that. So anyway, check the sidewall of your tire. It'll tell you. 35 is a good round number for most generic. If you're not racing or doing anything fancy with your tires, 35 is a good round number. But what is the actual pressure inside of a tire if it's inflated to 35 psi? So the gauge is reading 35. So we would have to add atmospheric pressure, which is 14.7, which gets me, 44.7 pounds per square, 49.7 pounds per square inch, right? That pressure on the sidewall of the tire is the gauge pressure, not the absolute. It's usually just scientists that are worried about the absolute pressure. And we'll get to situations in thermodynamics where we have to really worry about that. All right, let's take advantage real quickly of what we know about pressure and talk about hydraulic systems. This is a car lift, the kind of thing a mechanic would use to raise the car up to be able to work on it comfortably and safely. Hydraulics are found in a lot of different places. They're on doors. They're on if you have a car that's got like a hatchback, right, where the back opens up. Okay, you've probably, as you open the door, you probably heard the right? There's some gas cylinders that are on the side there that are helping you with the weight of the door. Anybody that's ever had one of those hydraulics fails knows exactly how heavy their door is, right? So what's going on there? The nature of hydraulic systems is an exercise in playing with Pascal's principle and pressure. This is not what hydraulics really look like. This is like a schematic. So basically what you've got is you've got a tube, and it's got a wide opening on one end in which sits like a table or a piston or something like that. And on the other side, there's another smaller piston. And so we've got like a cross-sectional area here. We've got a cross-sectional area that's bigger over here. And inside of this system, it's filled with something called hydraulic fluid. Now, hydraulic fluids in reality are like oily-based substances. But basically any fluid that doesn't change its density with pressure, like you can push on it and it doesn't change its features, is a good hydraulic fluid. Well, what we're going to do is we're going to push down with a certain amount of force on one side. And we're going to try and calculate how much force comes out the other side. And at first blush, you're like, well, Mr. Balogh, Newton's third law, right? Like, if two objects interact, the forces on them have to be equal and opposite. And that's true. But that would be true, say, for F1 on A1. But not necessarily F2 and A2, because what Pascal's principle tells us is that the pressure anywhere inside of a fluid at the same depth is going to be exactly the same everywhere. And so taking advantage of this nature of pressure, if we put pressure on side 1, we will get exactly the same pressure at side 2. We can toss in our definitions of pressure. And let's, for the sake of argument, just say that area 2 is 10 times bigger than area 1. Whatever the areas are, right? So, I don't know, 1 centimeter squared on area 1 and 100 centimeters squared on area 2. Doesn't matter, okay? But let's just say it's 10 times bigger. How much force are we going to get out of side 2 compared to side 1? It's going to be 10 times. So if I take this right here, right? This is F1 over A1 equals F2 over A2, but A2 is 10 times A1, isn't it? And so I've got A1 on both sides. I move my 10 around. This tells me that F2 is going to be 10 times more force than F1. So if I put in, say, 100 pounds of force on side 1, how much force am I going to get on side 2? 10 times 100 or 1,000 pounds. How do you lift up heavy cars? The answer is carefully. But after that, you use a jack. You use a hydraulic lifting device. The jack is designed to multiply through hydraulics the force you put in. So you slide the jack under, you get the long pole, and you start pumping up and down, okay? And you put in 20 to 40 pounds of push every time you push that jack lever down, but that allows the car, the 2,000, 3,000, 4,000 pound vehicle, to come up so that you can work underneath it, change the tire, do whatever you need to do. You pay a price though. Anybody that's had to jack up a car knows exactly what price you pay. You can lift the car, sure, but what's the price you pay? Huh? How far do you have to move this end of the jack? Like 6 miles, right? Of up and down movement, like going through like 4 feet of up and down movement for the car to go up, right? How, if I want to lift the car 10 centimeters and I have a 10 to 1 jack, how far do I have to move the lever? 10 times as far, right? So you pay a price in distance traveled, okay? You can't get something for nothing. But taking advantage of Pascal's principle allows us to lift very heavy things with a minimal amount of effort as long as we're willing to pay the price in length. Which is why if you have a hatchback car, right, or the thing lifts up and you see those 2 cylinders in there, right, they tend to be very long. Okay? They're trying to take advantage of, yeah, we're going to pay with length, but we're going to be able to apply some force as that hydraulic ram expands. All right. Not all hatchbacks have the hydraulics in them. Some of them just have very heavy springs in the hinges. let's talk about the world's first recorded wardrobe malfunction. Anybody heard of Archimedes? Huh? No? Yes? Archimedes screw, Archimedes burning boats down, Archimedes running naked down the street. Oh, now I've got your attention. Right? Archimedes was a Greek philosopher, aristocrat, old white dude, right? And he was famous for his natural philosophy and I suppose we could call it science. So one day, a local ruler, politician guy, came to him with a problem. The problem was, I've had a crown made for me, but I think the guy that made the crown is trying to rob me. He didn't make the crown out of gold. He made it out of lead or some other material, and then painted it gold or covered it in gold, and took the rest of the gold or something like that. It's politics. Nobody trusts anybody, right? And so he went to Archimedes and asked Archimedes to figure out whether or not the crown was made out of lead or gold. Now, I don't know this at all. There's no historic record of this conversation other than this was the request. I can imagine Archimedes just looked at the guy and said, look, melt it. If lead comes out, it was made, right? That's the answer, right? But apparently, it had to be some non-destructive way, right? To determine whether or not the crown was made out of lead or gold. So Archimedes has got this, he's got a word problem, right? How does he figure this out? And so he does what any self-respecting Greek rich guy would do when confronted with a problem of this magnitude. Huh? No, not yet. The running through the street happens later. No, he goes to the bath. He takes a... You guys know this, right? What has happened to classical education in America? I swear. What was the bath in Greek culture? How big is an Olympic-sized swimming pool? Big. Where do we get the dimensions for an Olympic-sized swimming pool from? The original bath. Baths in Greco-Roman culture were the equivalent of TikTok and Instagram today. They were the social hub. Social media was go to the bath. And we're talking huge pools full of water, surrounded by apartment complexes. You would go down to the bath and install yourself for 3 or 4 days, okay? And it would be a mixture of wrestling and getting all sweaty, muddy, dirty, and then for some reason they like to scrape each other off with sharp sticks, and then they would go jump in the water and get kind of refreshed, and then they would go out and wrestle some more in the street, and rinse and repeat, and you brought your household servants and slaves, and somebody had to peel the grapes, and it was a big deal to go to the bath. And you talked about things, and you argued about stuff, and you got all philosophical while floating around in a big pool.
2 questions. One, is this still the depth of an Olympic swimming pool?
Yeah, they were pretty deep.
Okay. Second of all, why were they so insistent on peeling grapes?
I have no idea. I made that up. But yeah, it just seems like something stuck up old white guys would do, right? So Archimedes goes down. And in smaller towns, they wouldn't be that big. There'd be a smaller community bath that maybe is a quarter the size of this room. But it was a big deal. Okay? And it wasn't just for hygiene. It was very social. And so he went down, and he's sitting there, and he's talking with people, and he's arguing natural philosophy, and he's got this problem, he's thinking about it, and he's watching people get in and out of the pool, right? And he's watching and everybody knows this, right? If you get a bunch of people into the pool, if everybody in spring break jumps into the pool, what happens to all the water in the pool? It flows out, right? You display, the bodies take up volume, and that water gets pushed out, right? But if everybody gets out of the pool, what happens to the water level in the pool? it just drops, right? So Archimedes is sitting there, right? He's thinking, okay, he's watching the water level go up and down, okay, as people get in and out of the pool. When all of a sudden, it hits him. Like, you've had these moments, right? That moment of realization, that moment when neurons like connect in a chain in your brain, and for that beautiful moment, you get it. You're just like, oh. My sister calls it the sudden rush of oxygen to the brain. Okay? It's just like this, all of a sudden, it hits him. He knows the answer. He knows how to figure out if the crown is gold or not. And he gets so excited. He jumps up and he starts shouting, Eureka. Does anybody know what Eureka means? It's Greek for aha, or I got it, or I figured it out, or yeah. He's shouting Eureka, Eureka, Eureka. He jumps up, he runs out of the bathhouse. He's running down the street screaming Eureka. And he had forgotten his towel. Apparently isn't all that big in ancient Greek culture. Naked guys running down the street happens every day, right? What had Archimedes connected? What had he figured out? This is called Archimedes' principle. The buoyant force. I think in your book they use F sub B, but I like capital B because it's nice and strong. The buoyant force, the force that holds up something when it displaces fluid, displaces water. So when you jump in a pool, okay, you can float there in that pool. Did gravity disappear? No. What's holding you up then? Not the air. My kids, so we would take them up to the mountains and let them play in the rivers and creeks and stuff like that. And when they were little, right, under 5 years old, they would love, I don't know what it is about human beings. If they see a river or a creek, they have to dam it, right? We have to exert some kind of control over the flow of the water, right? So my kids, they would pick up rocks and try to get the little creek or this thing, right? They try to dam it up and make a swimming pool or whatever, right? And it always happens, right? They start with small rocks, and then the rocks get bigger as they go, right? Eventually they're trying to like lift rocks that are heavier than themselves, and they can't do it, and they're smashing their toes and all kinds of stuff, right? But my kids discovered that if they picked up a big heavy rock under the water, that they could lift that. They couldn't lift it when they were outside the water, but they could lift the big heavy rock when they were in the water. And hilariously, they would try to get this big rock and they'd try to lift it up and they'd start to pull it out of the water. And as soon as they started pulling it out of the water, what happened? It got heavier. It didn't change its mass. Gravity didn't increase. But they brought it out of the water and they would, and then they would get pulled down into the water. Right, head down, diaper end up, right? You'd have to go in and, rescue them. Okay? Why does the rock get heavier as you lift it out of the water?
Buoyant force isn't acting on it?
The buoyant force comes from the water, right? The water is think of it like the normal force for water. It's like all of the water molecules are in contact, right? And there's going to be a normal force from those water molecules. And you add all that together and you get the buoyant force. The buoyant force points vertically upwards, okay? So the buoyant force is the force that's exerted by a fluid when an object displaces fluid, pushes the volume of fluid out of the way. What Archimedes connected was the fact that this buoyant force is equal to the weight of the fluid displaced. We write that as density times little g times volume. Let's unpack this. We know that the buoyant, I'm not responsible for spelling that word, buoyant force is equal to a weight of fluid displaced. Right? How do we calculate weight? If we know the mass of something, how do we find the weight? mg, right? So weight is equal to mg, right? Okay? So the buoyant force should be equal to this weight, should be equal to the mass of the fluid times little g. But we don't use mass of fluid, because that can change, right? We're going to use density instead. But we can't just swap m for rho. That doesn't work, right? But we do know that the density is equal to the mass divided by the volume. So what is the mass of something going to be in terms of its volume? It's going to be its density times its volume. So if we substitute in for that mass, then our weight becomes rho, the density, times v, the volume, times g. And then we just do a little bit of a rearrangement for rho gv. So that's why a density times little g times a volume in cubic meters is equal to a Newton, right? It's a buoyant force. It's still measured in newtons. All of those units will work together, but critically, the buoyant force depends on the density of the fluid displaced. That word means pushed out of the way. This volume is the fluid, like the amount of fluid displaced. So whenever anything is put into a fluid, whether it's at like the surface of the ocean or you sitting in this room, you are pushing the volume that is you of air is being pushed out of the way. The air and you can't be at the same place. So is there a buoyant force on you right now? Are you displacing a fluid? You are displacing air around you. So there is a little bit, teeny tiny, okay? Because how much does the amount of air that you take up, how much does that weigh? Itty bitty teeny tiny amount. So we don't feel that when we're in air. But when we jump into a pool, then we feel it. Why do we feel it in a pool and not the air?
We're very, very used to it.
No. What's the difference between air and water? Density. Okay? Air is like 1.29 kilograms per cubic meter, and water's 1,000 kilograms per cubic meter, right? Water's 1,000 times more dense than air. And we are mostly made of water. And so it should come as no surprise that our density is actually a little bit less than that of water on average. And so we tend to float in bodies of water. We float with about like 95% of our body below the water, so you gotta be tricky and keep your breathing holes above the surface. But the weight of water that gets pushed out of the way when we enter the pool is about the same weight as you. How do boats work? What's like one of the main features of a boat? It floats. Because if it's not floating, it's not a boat anymore, right? It's not even a submarine anymore. It's a shipwreck, okay? Because technically, if you talk to submariners, a submarine is a boat, according to them, right? So, boats float. Usually we think of boats floating, say, on like the surface of the ocean, right? Okay, that's a sail. And that's a pirate, and you can tell it's a pirate because it's got a feathered hat. Okay, so Boats float. Why? What do we know about the total net force on a boat if it's just floating there? It's in equilibrium. It's not accelerating up or down, right or left. It's in equilibrium, meaning that the forces on it have to add up to 0. Does the boat have weight? Is gravity pulling down on the boat? Well, yeah. Okay? But that weight, we know, has to be counteracted by some force. And if the boat's in water, what is the force that's going to be acting upwards? The buoyant force, right? Buoyancy. And so, that means that the buoyant force acting on a boat has to be equal to the weight of the boat. But the buoyant force is the density of the fluid displaced times little g times the volume of the fluid that's displaced. The mass of the boat, using this trick where we can swap mass for density times volume, would be density of the object times g times the volume of the object. That's object, okay? That is below the water. It's not the total volume of the object. Actually, it is the total volume, sorry. That is the total volume, because the mass is the volume, the density of the object times the volume of the object. But let's take a look at stuff that cancels out here. What's the same on both sides of that equation? Little g. So in other words, what we just solved is how to float things anywhere. This is how to float something in your bathtub, in a backyard pool, in the ocean, in the air, on Mars, Venus, Jupiter. Pick your place. We just solved it. Because it's independent of the amount of gravitational force exerted by those objects. What are we left with? Volume of fluid, or density of fluid, volume of fluid equals density of object, volume of object. Okay. What is this relationship trying to tell us? Trying to tell us lots of things. What happens if the density of the object is smaller than the density of the fluid? In other words, this number right here, density of an object, is small compared to this one that's big. So like it's like this right side is getting smaller, but this left side is getting bigger. But we need an equal sign, don't we? For something to be floating, these things need to be equal. So what compensates if the density of the object is low, but the density of the fluid is high? The volumes are going to switch around, aren't they? And which one's going to get bigger? Which one's going to get smaller? This one's getting small. So this is getting big. So volume, it's like the ratio, the amount of volume to fluid to volume to object is going to get less. In other words, if I put a styrofoam ball in a pool, it's just a little tiny bit of that ball goes down into the water. Again, the buoyant force only needs to be equal to the weight of the object. Styrofoam doesn't weigh very much. Styrofoam has a density much less than water. And so let's say styrofoam has a density of 5% that of water. It's only going to have 5% of its volume submerged. But if we put something like a block of ice in the pool, ice has a density that's approximately 90% that of water. How much of the ice is going to be below the water? 90%. And only 10% will be above. What happens if we try to throw like a bowling ball in the pool? Is it going to float? No. It's going to sink. And why is it going to sink? Its weight is going to be bigger than the buoyant force's ability to hold it up. Remember, the buoyant force is limited by the weight of fluid displaced, and a bowling ball displaces not enough water to float it. In other words, it's more dense than the water that is around it. Let me show you this video.
We'll use these 3 blocks of wood to demonstrate how density affects the depth at which objects float. This block is cut from balsa wood, with a density of about 0.14 grams per cubic centimeter. When placed in water, it floats with only about 1/7 of its volume submerged. This is a block of pine, with a density of about 0.5 grams per cubic centimeter. It floats with about half of its volume submerged. This is a block of ironwood, with a density of about 0.9 grams per cubic centimeter. When placed in water, it floats with about 9/10 of its volume submerged.
But all of those objects are floating because they're in equilibrium. Sinking is not equilibrium, okay? Sinking is going down. All right, I want to show you a video. Now, the contents of this video don't matter. I've been showing you clips from a series of ancient DVDs called the Encyclopedia of Physics Demonstrations. They're very handy when you have a low budget like we do at community colleges. We can't get all this equipment. They film it for us, and then we can play it. The DVD set is 26 discs. That's a big DVD set, right? And on each DVD, there's anywhere from 12 to 28 demonstrations. So there's literally hundreds of these videos, right? I picked the best ones. Everywhere in these videos, you see poor, starving physics graduate students being made to do experiments, right? And I'm convinced that they've been told to not smile. This is science, serious. Don't smile. Don't look like you're having any fun. So with all of that in mind, knowing that I have watched every single one of them, let me show you my favorite.
We're used to seeing objects floating in large amounts of water.
Yeah.
But how much water is actually required to float an object?
Why do I care?
We'll use this wooden block to find out.
Great.
This container is just barely larger than the block.
That's
and
exciting.
has a small amount of water in the bottom.
Uh-huh.
When the block is placed inside,
Ooh.
the small amount of water is enough to float the block.
Okay, fine. Yay.
The
Water
amount of
floats
water
things.
required to float an object is just enough to actually surround the object in its container.
Okay, great. Wait, what?
In a container of the right size, a large
Watch this
object,
end of the boat.
such as this ocean liner, could also float in a small amount of water.
What just happened?
Genocide.
I kid you not, 200 and something odd things, right? Okay, 400 and something odd things. Not once, anywhere is anybody like smiling, looking like they're having fun. Serious physics. And then this? I think this is evidence that somebody cracked under the pressure, right? The graphics department had had enough. And they were like, we're gonna stick an Easter egg. But this is as far as physics graduate students can go in terms of, being rowdy, I guess. It was just weird. I remember the day that I saw that. I was like, what? What is going on? All right, I will do an example of Archimedes' principle on Thursday. You should be able to get some start on your homework. We'll finish up fluids on Thursday. Exam autopsy tomorrow. See you then.